We studied variational autoencoder and generative adversarial network (VAE) and GAN as generative model. So where we have latent variable Z or latent vector Z, and we have decoder network or generator network, and essentially we pass the latent vectors through the generator or decoder and have a new image or new data. And the main goal of VAE and GAN generator or decoder is essentially from some very simple latent space and using very simple distribution like a normal or sometimes uniform. You draw a real data generative model. It looks like the real data which already we observed or we collected from real world scenario. Okay, so where for GAN, essentially at each time we randomly sample a latent vector and pass through the generator. So this is the case of GAN, GAN, and then observe some value y and see where is the location of y and measure the distance between this y and all the other real data points using some discriminator network. So discriminator essentially learn the manifold of real data set using the randomly generated data and all collected data set, which can measure the distance between your generated data point and the real data manifold. Yes, so this is how we train the GAN. Essentially, we always learn the discriminator, which measure the distance between your generated data and the real data manifold. And also you try to optimize your generators so that every time your randomly generated y value close to the real data manifold. Okay, and VA basically pick a data point we already have in our real data set and using encoder we make a latent variable corresponding to the real data point on the data manifold, and from this latent variable or latent vector you generate new data point, let's say y hat, using decoder and measure the distance between the y and your corresponding real data point y hat and y. And essentially here we try to optimize your decoder network so that your y hat close to y. And also for the variational autoencoder we have to design the decoder network so that when you randomly generate a latent vector from very simple normal distribution, then the output y hat located near the real data manifold. So for this purpose we introduce some KEL divergence cost function, which between the QZ for given xi and the very simple normal distribution zero mean and identity covariance matrix when you train your decoder and encoder network. So this was your variational autoencoder and GAN network for your generative model. Normalization flow, another approach, normalizing flow, sorry. which essentially try to learn the distribution of py directly from pz. So pz is usually a normal distribution with mean zero and identity covariance matrix. So you randomly generate a very simple normal distribution and you pass through some neural network and you get the output y. And from the simple distribution pz and the neural network structure, we can understand the distribution of y directly from your neural network and the right-hand distribution if the neural network follows some rule. Okay, so normalizing flow utilizes such a special neural net architecture, and we can understand the distribution of y directly from the structure. So why this is useful? Because we can understand py directly. Essentially, if you if you solve log likelihood, maximum log likelihood function, so if you maximize your log likelihood value by optimizing your neural net parameters, then maybe your neural net is very nice generative model for your normal random right-hand variable. Okay, so to understand normalizing flow, we have to understand change of distribution first. Sorry. Change of distribution. So change of distribution is very simple. If you want to compute the distribution of y from qz, distribution of z, essentially, and if the y and z follow this function where f is LD to LD, so let's assume the latent vector and the output vector share the same dimension. Then the QYY, so the distribution with respect to the output y, a distribution of output y, is equal to the distribution of your latent variable times the determinant of the Jacobian inverse matrix of F. Or this is equal to QZZ determinant Jacobian of the original function f inverse. Okay, so this is a very simple normalize the change of variables in probability distribution. So why this is true? What is the intuition behind this equation? So let's consider very simple 1D input and one-dimensional output case. And let's consider very simple function like this. So this is y equal to fx function. So here, when you consider, so this is x and this is y, delta amount of range on the x-axis, then what is the corresponding value range of y? This is the corresponding value range y. Let's say this is epsilon. So the distribution for this area is delta, roughly, when delta is very small, delta times px. Okay, so because we just use function f for the change of variable. Okay, so this is so change of variable. this should be equal to epsilon times py. Of course, this distribution defined for your variable x, and this distribution defined for your distribution y. And the two distribution px and py have to follow this rule. Okay? So this is, so pxx was equal to epsilon over delta pyy. Pyy was equal to delta over epsilon pxx. Right. And what is epsilon over delta? And what is delta over epsilon? What is epsilon over delta? Delta over epsilon, which is essentially equal to delta over epsilon, which is essentially sorry. Okay. So from this property, we have this result. Sorry, this is y. Okay. Alright, so why this is important? So from this property, what we can know is the determinant of your function. So for instance, in this case, in this neural net case, if you have a latent variable g1 and you sequentially generate a new latent variable all the time, and then make your output y. Important thing is determinant of your Jacobian function. So if you define f1, f2, sorry, I have used another notation. If you define f1, f2, f3 to define the connection between z and z1, g1 and g2, the important thing is how can we easily calculate the determinant of Jacobian, and the Jacobian of here and so on. So basically this means determinant of f delta z. Okay, f1 and determinant of Jacobian okay. So when you keep the same dimension RD for each layer, for every layer, and you define very simple function f1 and f2, f1, f2, f3, and so on, so that we can easily compute the determinant of your Jacobian every time. The property of y, py, is just the product of Jacobian times pzz, and the pzz is very simple normal distribution. Okay, so if you want to understand the probability measure for your given image or given data, what you should do, what you have to do is you just need to compute the inverse function, so that you can understand what is the corresponding the latent vector for your output y. And then you have to calculate the Jacobian for each layer so that you can calculate this part. Then you can get the PYY, the distribution of Y. So this is why the normalizing flow is very useful. Okay? If you can design a neural network so that each layer has very simple shape, so you have very simple determinant form and very simple inverse function, then from the output Y, you can easily understand each layer's probability shift, and you can very easily understand the distribution of output Y. Then how can we easily compute the determinant of Jacobian? So here, most important thing is determinant of Jacobian usually not easy to compute. Okay, so what is determinant? Determinant is product of eigenvalues in general. And product of eigenvalues is not easy to obtain with general form of matrix. Okay, so if you don't have any restriction on designing your neural network and with very usual weight matrix W, it is extremely difficult to understand the determinant of the Jacobian between two layers, because the Jacobian defined with the weight matrix and the gradient of your activation function usually, and the determinant of weight matrix is not easy to calculate. But one nice property of triangle inequality can resolve this issue. If your matrix is lower triangular, so which means all this side filled with 0 and only this side having non-zero element, or if your matrix having non-zero element only this side, this upper triangle side, and all this side having 0 values, then the determinant of the matrix just product of diagonal term. Just product of element of diagonal term. Okay, so that is very important thing. If your Jacobian follow these two shapes, then we can very easily calculate the determinant from the diagonal terms. Okay,